6-6 will take us a really probably good solid 3 days to get through because of the material that's thrown in there. It's not that there's a lot of material, but the material that we get thrown into it becomes why does math math? That's kind of what happens when we get to 6-6. And then 6-7 puts everything back together with like, why did we kept saying that if you have a fourth degree polynomial, you only have 5 terms. If you have a fourth degree polynomial, you can have up to 4 zeros. Fourth degree polynomial, you can have 3 changes in directions. You can do your tails and do all other stuff. So that's where all of that comes to a head in a 6-7. And then that'll probably be about 2 weeks from today after all the break and all that. And then we'll do 6-8, which is some light modeling, which will be the following Monday, Tuesday. What stinks is that we only have like 3.5, 4 sections left to go, but it's going to take 3 weeks to get to it because of the days of this, with November and all that kind of stuff. So, excuse me. So let's take a look at what's called remainder theorems and factor theorems and all that. But it also stems from remembering what in the world this crazy little thing called long division looked like. For example, dude, no way. It's okay. You're going to learn today. So, lattice, ew. You can't lattice with like fractions or anything. Ew. No, unlearn it. If any of you have ever learned lattice, exactly. Yes, unlearn it. It never existed. It never existed. Okay, lattice this. Okay, there you go. All right, anyway, so refresher course or learning course upon what long division meant. And when we're using long division, the reason why we bring it back up here with polynomials is because there are certain things that occur with polynomials that we use long division to figure out. What you're trying to do is you look at what you're dividing by 13. You're taking 27,419 divided by 13. So what you're doing is you're asking yourself the following questions. Does 13 go into 2? No. Does 13 go into 27? How many times? Twice. Okay. If I put a 2 above the 7, because it's the tens place. Okay. What's 2 times 13? 26. I write that here. I multiply and then I subtract. And I bring down the 4. Does 13 go into 14? How many times? 1. 1 times 13 is 13. Subtract it out. Bring it down. Very good. Does 13 go into 11? No! No, it does not. So I got to put a 0 here. Which means I have to, which means I have to bring down the 9 then, because this becomes a 0. Subtract it out, we get a 119. So, 13 into 119. This is where you have to start thinking a little bit larger scale. I know 13 times 10 would be 130. If I back out 13, I get 117. Oh, so it's 9. Okay? So I do put a 9 here, and I get a 117. Oops. Well, here's what happens. For us, what you guys are used to doing, then you would get your decimals, and then you'd figure out your decimals where it ends out. Well, this value of 2 is technically a remainder, right? Now, remember you guys used to do that if you had a remainder when you first learned, you would write R2. That's kind of the cheap way of doing it, isn't it? But remember, that value of 2 is a fractional amount of the 13. So it's like, so it's 2109 and 2 13ths is what we would have said. Do you vaguely remember that now? Well, the process by which we do this, by looking at Does 13 go into 2? Does 13 go into 27? And so on. The process by which we do this does not change whatsoever when we look at it in terms of polynomials. For example, I have 2x plus 3 into. Now, when I do long division, just like we said before, like when we did the synthetic substitution, remember how I always said make sure you have placeholders? Same thing happens here. You always have to have placeholders just in case. So I'm looking at it. I have a 2x plus 3. That's fine. It's a variable, then a constant. There's no upper degree things to worry about it. But what I'm dividing into, I have a cubed, squared, x, and a constant. Third degree polynomial, I have 4 terms, so do I need a placeholder? No, so I just write it out. Here's a top tip. Space it out a little bit. Spacing it out a little bit, it gives you a little bit more room so you don't get lost in your handwriting. Not to say that some of you guys have bad handwriting, but just saying. And then I go through the same idea. Remember a minute ago when we said, did 13 go into 2? You guys said, no, but 13 went into 27. So what I'm doing here is, instead of doing that, when I'm working with polynomials, I want to eliminate the first term each successive time, which means I got to figure out what do I multiply 2x by to turn it into a 2x cubed. Just x squared. Now, take a wild and crazy guess what you're going to put the x squared over. The 7x squared. You always line up what you're multiplying by up here. I'm going to say I'm multiplying it by x squared, and line it up above this. The reason I do that is because now I have 2 terms on the outside, and I'm going to have 2 terms on the inside. Because same thing, I multiply the x squared to here, and I get 2x cubed plus 3x squared. I'm just distributing that back. Let's just write x squared. Okay. What do you multiply 2x by to turn it into a 2x cubed? I multiply by x squared. I write it up on top and I multiply it back in, just exactly the same way I did here. I multiplied 2 times 13, gave me 26. The only thing that's different is that there's variables involved. Okay? So now I subtract it. 2x cubed minus 2x cubed, gone. Negative 7 minus 3 is negative 10. Woo. And then I bring down the negative 17x. And then I start over again. What do I multiply 2x by to turn it into a negative 10x squared? Negative 5x, good. Distribute the negative 5 to both parts. You get negative 10x squared minus 15x. The 10x squareds go away because it's negative 10 minus a negative 10. Negative 17 minus negative 15 is negative 2x. Bring down the negative 3. What do you multiply a negative 2x by? What do you multiply a 2x to turn it into a negative 2x? Negative 1. And it works cleanly. Now, if you think about it, what we just did, since our remainder here was 0, what our remainder is here was 0. We went from, I'll put this here real quick, I'll come back to it. We took this part here, the 2x cubed minus 7x squared minus 17x minus 3, and we were able to break that down into saying that it was 2x plus 3, I think. And what were we left with again? Minus 5x. Now, what you're able to do is you actually factored out a 2x plus 3 because your remainder was 0. So what happens here is you think, if you go back to this was 4 terms. That's not factorable, is it, by GCFs? You can't do that. So by using long division, by using certain parts, by learning how do you get through terms and zeros and things, you're going to be able to figure out different ways to factor what you once thought were unfactorable. That's why we learn this stuff. Okay? That's why we get there. So back to this again. Remember, that means that 2x plus 3 is a term of x squared minus 5, or excuse me, of 2x cubed minus 7x squared minus 17x minus 3, because I'm left with that. So if I multiplied these two guys together, if I multiply those two guys together, I'll get that 2x cubed and so on. Right? What's the answer? Oops. The answer is this. What if there was a remainder? Let's say there was a remainder. Let's say the remainder down here, just for easy, let's say it was 9. Let's just say the remainder wound up being 9. What do you think you would have written it as for a remainder? Yeah, it would have been all this junk plus 9 over 2x plus 3. Yeah. And there's a reason why we worry about remainder stuff later on. We've discussed this before. Regular old boring asymptotes are ones that are vertical because you can't divide by 0 when you have certain polynomials and rational expressions. Well, what's going to happen here in a little while, well, not this chapter, but probably in about a month or so, we'll have slant asymptotes. And you've already done this. You did this with conics, with hyperbolas. Hyperbolas had slant asymptotes. But they also occur in rational expressions, which deals with this as well. So this is just a little precursor to when you have to see this a practical way for it, but it's just kind of a long way of getting. Let's try another one. Oops. I have 2x to the 4th plus 3x cubed plus 5x minus 1. And I want to divide that by a trinomial, x squared minus 2x plus 2. All right. Now, as you're writing these out, it's giving you in descending order a 4th degree polynomial. A 4th degree polynomial should have how many terms in the polynomial? Does it? What is it missing? So what do you put in place of it? A 0x squared. Yes, you always put placeholders in, whether it's in the divisor or the divisee, or inside the symbol or outside. Dividend, which one's that? Is that the outside or the inside? The outside? I always forgot. Thank you. Verify. So I put in here 2x to the 4th, 3x cubed, 0x squared, 5x minus 1, x squared minus 2x plus 2. And again, you just go through the process. What do you multiply x squared by to turn it into 2x to the 4th? 2x squared. Where do you think you're going to place that over? Over the 0x squared. Distribute that through, you're going to get 2x to the 4th minus 4x cubed plus 4x squared. And once again, what do I do to all three of those parts? Subtract all of them. I don't care about updates. Stupid. Sorry, Devin, it wasn't your fault. What'd you say? Okay. Okay. Don't sound so exciting. Or excited. Okay. All right. What's 2 minus 2? 0. 3 minus negative 4. 0 minus 4. And then I bring down the plus 5x. Hey, what do you multiply x squared by to get 7x cubed? See how it's lining up above everything this way, guys? Because there's order in the chaos of math. Got teacher ears, of course I heard that. But my wife says something, what? You'd be surprised how fast you can hear an F-bomb drop. Sam didn't even move. No, I know, I'm messing with you. I'm just messing with you. Subtract them all out. You get negative 4 minus negative 14, you get 10x. Hi! Are you super excited we're doing long division? Good! And then, what was our constant? Bring down to 1. Negative 1, thank you. And then lastly, what I want... Smug, aren't we? Lastly, what do we multiply x squared by to turn into a 10x squared? Multiply by a 10. That 10 to the negative 20. So subtract. So we get 11x minus 21, I believe. Okay. Now, my remainder, I know that this is going to be my remainder because it is 1 degree less than what I was dividing by. Okay. So now, since that's my remainder, I just write it as, is it a positive 11x or a negative 11x? Positive. So I just write it then as plus 11x minus 1, thank you, over x squared 2x, sorry. And that's what we do. Remember, it's not that it's a horribly difficult thing, but it's there. You have to be very precise in how you lay it out. Right? Now, long division, like I was saying, has its place for us as we get along into higher degree things with a little bit more of the rational expressions. We still use it pretty often in here. But I think the other thing that we're going to start to use even more so is this thing called synthetic division. Okay. And when we talked about this a little bit before, remember when we did synthetic substitution, that you would write it out with that little backwards upside down L, and you put your coefficients in and all that? We do the exact same thing, and for right now, for the first few sections or so, first few days of doing this, they're going to give you specific terms that they want you to divide by. Remember, terms would be things that are in parentheses. So x minus 2 is a term. What's the term x minus 2's 0? 2. So the 0 would be the 2. If x plus 3 is a term, what would be its 0? Negative 3. That's what it means to divide by the 0. Remember how I had this big talk with you guys throughout quadratics and earlier on, where we distinguish the difference between terms in parentheses and then zeros? If you have a 0 of negative 5, that means you have a term of x plus 5, and so on. So what we do here is the same thing. I look at x cubed plus 2x squared minus 6x minus 9. And what I want to do is use all of its coefficients, as well as any placeholders that might be needed. In this case, I have a third-degree polynomial. I should have 4 parts to it, do we? Okay. So we start out by this. We have a 1, 2, -6, and a negative. And I'm going to first divide out by the 2 because it's asking me to do synthetic division with the x minus 2. X minus 2 is a term. 2 is its 0. Remember? All right. Do you remember what the first step was with synthetic? Drop the 1. Good. So I drop the 1. What do I do with the 2 and the 1? Then where do I write it? What do I do now? You're almost there. You're halfway there. If you subtracted the negative, I'll stop talking. Multiply on the outside, add on the inside. So drop the 1, 2 times 1 is 2. 2 plus 2 is 4. 2 times 4 is -8, or -6 plus 8 is 2 times 2 is -9 and 4 is. Now, since this did not land or end with a 0, since this didn't end with a 0, that means that 2 is not a 0, which means x minus 2 is not a term of this function. Okay? That means that you could not factor out the term x minus 2 from it. So what you do then is you try it again with the next one. Eventually, you'll learn how to choose your own possible zeros, but for today, they're going to give you zeros to try. Yes, ma'am? How it's not a possible 0? I didn't end in the 0. My last, if this is a divisible thing, that means that my last term would be a 0, which means -5 just means I have a remainder, my leftover. Okay? So if I change this up and I do this all over again with, what was it, -3? If I change it up with just with the -3, obviously, again, the first thing I'm going to do is I drop the 1. Hi, Siri. Oh, she. Oh, whatever. -3 times 1. 2 plus -3. -3 times -1. -6 plus 3. -3 times 3. Okay. Now, remember what that means now. If I end in a 0, that means that -3 is a 0 of this function. If -3 is a 0, what's its term? X plus 3. So that means I was able to factor out an x plus 3 from the original x cubed to x squared minus 6x minus 9, which means these all went down 1 degree. These are now the coefficients of the next trinomial. X squared minus 1x minus 3. This is how you factor higher degree polynomials. You are looking for zeros of a term. Dividing is factoring. Dividing is factoring. It's another process by which you can do it. Okay. So as you go through this, what we're looking at is whenever you find a 0, and when I say find a 0, that means that last part of your synthetic division is a 0. That means that, in this case, the -3 has a 0. Its term was the x plus 3. And what was left over after you were able to divide that out, drop the degree. The exact same way that if we would have done long division, this would have been up top. What do you multiply x by to get to x cubed? X squared, and so on and so on and so on. And that's how that would have worked. Okay. Let's do synthetic on this. Let's do synthetic on this. X plus 4 is the term, which means it's 0. So you have x to the fourth minus 16x squared plus x plus 4. You have a fourth degree polynomial, which means how many terms should it have? Should have 5. Doesn't have 5 in there. Where do I have to put a 0 for a placeholder? At the x cubed. So I start out with my 1, 0, negative 16, 1, and 4. Now I want to use synthetic division from the term x plus 4, which means I divide by its 0. The 0 of x plus 4 is negative 4. Okay? Procedural. Drop the 1. 1 times negative 4. 0 plus negative 4. Negative 4 times negative 4. Negative 16 plus 16. Negative 4 times 0. 1 plus 0. Negative 4 times 1. I will break you. So is negative 4 a 0? Yes. That means negative 4 I was able to factor out the term x plus 4. So negative 4 is a 0. As we go through some of these things, you might start to pick up on when I say that negative 4 is a 0, notice I'm circling it. And then I automatically say, if negative 4 is the 0, what's its term? So I have x plus 4, which means this was dropped by 1 degree, which now makes it x cubed minus 4x squared, 0x plus 1. So I was able to factor out of that x to the fourth minus 16x squared plus x plus 4, I was able to factor out the term x plus 4. Yes, ma'am? Every time you divide out a factor, every time you come out and take out a 0 like that, you drop 1 degree. Every time you divide something out like this, you drop it 1 degree. Yeah. So what's going to happen here over the course of tonight, and I'll put these up here for you here in a second, is that I'm going to ask that you guys do some long division problems and some synthetic division ones. Long division, just write it out. If there's a remainder, put it over the fractional. Synthetic division, if you find a 0, get in the habit of rewriting it with dropped degree next to it for the next part, because as we build into this dividing out with synthetically is going to allow us to continue to factor as we go along. But you're just going to constantly synthetically divide, because it becomes really, 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 really fast. Okay. If there's anything else I wanted to show you. I didn't want to get too far into this. For these, I think the ones you're going to do tonight, you're just going to test a couple of them. And if it doesn't get a 0, if it doesn't wind up on 0, you don't do anything. It just means you did it and you just leave it. That would technically be your remainder, but I'm not going to have you guys write it out synthetically. The benefit for synthetic division is going to come when we get to something that looks like the benefit of synthetic division is going to be when we get to something like this that I need you to find all the zeros. Because if I look at that right now, I'm going, No. But as I learn about how do I work with my tails, in this case, I'm going to be able to test it at, what is it, 1, 5. I think it's just 5 would be 21, 105. Whatever. There's a whole bunch of stuff you can wind up testing it out on. But as you learn how to work with all the possible rational roots that you can have, you can zip through synthetic division real quick. And you'll be able to tell right away if you're going to get a 0 here or not, and then you'll be able to drop degrees and become something more factored. This is how you factor stuff that looks like crap real easily. But it stems from learning how to do it this way. Tonight, or throughout the next day or so, I'd like you guys to work on, this is on page 356. I've got, what, 6 long division and 6 synthetic. Yeah. So this is on 6.5, page 356, 1537 dots. Okay? Remember, whenever you're doing long division or synthetic division, you always have to have placeholders. When synthetic division comes around, you'll notice that you're only going to be synthetically dividing with a degree of 1, because that's all you can ever do. You can't synthetically divide with trinomials or anything. It's only going to be first degree polynomials. But when you do long division, you always have to have placeholders. For real quick, if you look at number 25, sorry, it's kind of blurry on that one. You see it's a 5x to the 4th, 14x cubed plus 9x. This one needs 2 placeholders on one side. X squared plus 3x needs a placeholder at the 0 as well. So even though it's plus 0 for the constant, or plus 0 on the dividend, you still have to have it there. The reason you have to have placeholders so you don't get garbled up in the middle. All right? Space it out, write it a little bit wider, and go from there. But yeah, go ahead and get started. You probably knock out a good 4 or 5 of these things here. Yes, ma'am. No matter what, you always want to have you have to have a placeholder, so it would be okay. Because as you're multiplying through, you'll have that plus 0 that you have to bring around to it.